Hi, geometry folks. We're going to continue with Unit 3, and we're going to start on page 39 in your book. A couple of the books may have page 41, but it's the page that looks like this. It says Lesson 4, Scaling Principles, and it starts with a triangle like this. All right, so we're going to be talking today about volume. So we're going to be moving into 3 dimensions, 3D. So we were talking about flat figures that just draw on a piece of paper. Today we're going to add another dimension, and we're going to start talking about what are called solid figures, okay, that are shaped like boxes or cans or cones or something like that. All right, so we're starting off with two-dimensional figures. So we have here 2 triangles which are similar. This wave symbol means similar. That means they're not the same size, but they are the same shape. It comes from a transformation called a dilation, which means that all their measurements, all the lengths, are multiplied by the same scale factor. All right, so let's just talk about what those factors might be. So in this first one, we have a large triangle A and a small triangle B, and they've already written down the corresponding side lengths. So the height of 6 corresponds to the height of 4 on the other triangle. The base of 3 corresponds to the base of 2. So we have a ratio of 6 to 4, or 3 to 2. Now their areas are not going to have the same relation because the areas have 2 different dimensions, not just a single dimension. So the area of the large triangle, if you remember, 1/2 times base, 3, times height, 6. 1/2 of 3 times 6 is 9, 1/2 of 18. The small triangle, the area is 1/2 of 2 times 4. Which is 4. So the areas comparison would be area of 9 compared to the area of 4. And here's what's interesting. The lengths, the comparison is 3 to 2. The areas, the comparison of 9 to 4, you guys, 9 is 3 squared and 4 is 2 squared. Look at 3 to 2, 3 squared to 2 squared. Let's look at a rectangle. We have a small rectangle A and a large one B. The area of the small one, if you remember, for a rectangle is just base times height, 3 times 1, length times width, right? 3. The area for the large one, 15 times 5, which is 75. Let's do some ratios. Let's compare the small one to the large one. When we look at the lengths of the sides, 3 compares to 15. 1 compares to 5. Okay. What about their areas? Because the second column is areas. Well, the area is 3 compared to 75. All right, that doesn't look like anything here, but we can simplify. Just like you can simplify a fraction or an equation, we can divide these by the same number. We can divide them both by 3, and we get 1 to 25. Well, you know what? 1 is 1 squared. 25 is 5 squared. Oh, look. 1 to 5, 1 squared to 5 squared. We can do one more super quick. Triangles here. This time we're going from a large one to a small one. The area, 1/2 base times height, is going to be 20. And on this one, 1/2 of base times height is going to be 5. All right. Comparing the corresponding sides, 10 compares to 5, 4 compares to 2. And you can see that we could simplify that to 2 to 1, right? This one is always twice that, twice that. Look at the areas. The area is 20 compared to 5. We can simplify that divided by 5 is 4, divided by 5 is 1. 4 is 2 squared. 1 is 1 squared. 2 to 1, 2 squared to 1 squared. These are two-dimensional objects. These are 2 dimensions. You know how we talk about 3D? These are 2D. They only have a length and a width. They don't have another measurement that goes up and down, right, like a height. So 2D means the scale factor is in 2 directions. So we're multiplying times 2 this way, and we're multiplying times 2 that way. All right, so you know what? What happens? What would happen if we changed that to 3 dimensions? So if you go on to page 41, a couple of books are page 43, but most of you should be on page 41. We're going to talk about volume now, which is like what fills the inside of this 3-dimensional figure, right? Like a can or a box or something. What's the space inside of that box? And so the volume formula is basically the area of the base shape, whether it's a triangle or a rectangle or a square or a circle, the base area times the height of that figure. Okay, so we're not going to do the cone. That will come in the next lesson. But we will do this box shape, which is called a prism. A prism is any 3-dimensional figure that has a 2D figure, a 2-dimensional figure as a base, and then the sides go straight up from the bottom to the top. So you can see that this one starts out as a rectangle on the bottom, just your typical box, right? And this is a rectangle on the bottom with sides. And the length is 15, the width is 5, and the height is 10. The little one, the length is 3, the width is 1, and the height is 2. So we can compare all the corresponding sides, small to large, A to B. So we'll compare 3 compares to 15. Those are corresponding. 2 compares to 10. And 1 compares to 5. Those are corresponding. Now the volume, remember the volume is the base area times the height. So for the little one, the volume is going to be the base area. Well, that rectangle on the bottom, the area is just length times width, 3 times 1. Then we multiply times the height. So the total volume is 6. For the larger one, the base, the rectangle on the bottom of the box, is 15 times 5. And then times the height, which is 10. So that's going to be 750. So if we write a ratio comparing the volumes, the small one is 6, the large one is 750. And again, just like we did on the other page with the areas, we can divide both of these numbers by the same number to simplify it. We can divide them both by 6. This is going to become 1. 6 divided by 6 is 1. 750 divided by 6 is 125. So I'll tell you guys something. This is 3D, right? These are 3-dimensional figures. They have a length, a width, and a height. So that means we need 3 factors. We need times 3 this way, or times 5 this way, times 5 this way, times 5 this way. And you know what? 125 is 5 to the 3rd power. 5 times 5 times 5. 1 is 1 to the 3rd power. 1 times 1 times 1. See pattern? Whatever this relationship is, whatever this ratio is, you raise them to the 3rd power because these are 3D. On the area, we raise them to the 2nd power because it was 2D. It was 2-dimensional. Okay? We could do the same thing on the back of this page with a triangle. the area of the small one would be the area of the base. Half of 4 times 6. Half of 4 times 6 is 12. And then the volume would be the base area 12 times the height of 12 for a total of 144. For the big one, the base area is 1/2 times 18 times 12, which is 108. And the volume would be the base area of 108 times the height of 36, which is a really big number. It's 3888. Okay, so what happens is that for the volumes, it's 144 for the small one compared to 3,888 for the large one. Again, you guys, we can divide them both by 144. 1 compared to 27. Well, what was the relationship of the sides? 4 to 12. 4 times 3 is 12. 6 times 3 is 18. 12 times 3 is 36. So for the side lengths, the ratio was 1 to 3. For the volume, 27 is 3 to the 3rd power, 3 cubed. Okay, that's the pattern. Okay, so your volumes are going to go up because it's 3D, means the volume changes by scale factor to the 3rd power. Okay, so that's the rule that you should be keeping in mind. All right. So let's solve a problem. Let's do something a little bit different. Let's go to page 43 or 45. Just look for this problem. And you've got a triangular prism. It's a triangle base, straight sides. And let's start by calculating the volume of this prism. Okay, so the base area, 3, height is 3, the triangle height is 3, so it's 1/2 times 3 times 3. The height from the floor, from the bottom to the top, is 5. So this is going to be 1/2 times 9 times 5, which is 22.5. Now, talking about scale factors, what if what we have is not a dilation? The measurements don't all change by the same factor. What if one side changes by a factor times 2, one side changes by a factor times 4, and the height changes by a factor times 3? So what's going to happen is this one is going to change to 6, 3 times 2. This one is going to change times 4, so that's going to become 12. And the height changes by a factor of 3, so the height becomes 15. All right, let's see what happens to the volume. So the volume is going to be the base area times the height. The base area is that triangle, so it's 1/2 times 12 times 6. And then we multiply times the height, which is now 15. Okay? So 1/2 times 12 times 6, this is the volume. That's 36 times 15, which is 540. Okay? So what are we thinking? If they all changed by the same scale factor, we would just change the volume by that factor to the 3rd power, right? We times that factor, times that factor, times that factor. This one changed by 3 different numbers, but that's okay. We can still do that. Look at, oops, I'll do it down here. We can take our original volume, 22.5, and how does it change? Well, one side changed times 2, one side changed times 4, the height changed times 3, And do you know what? All that together means times 24. 22.5 times 24, guess what? 540. Okay, so in this case, we did not have a common scale factor. So our volume didn't change by a scale factor raised to the third power. Our volume changed by a multiple of each of the three factors. You have to include all three of the factors. If they were all the same, like if they were all 2 and 2 and 2, then it would be times 2 times 2 times 2, which is 2 to the third power. But these are different, so you just do each one as a separate factor. Okay? There may be a problem like that on your problem set, so if you need to watch that part again, watch that part again. All right, so we're going to talk about cylinders now. A cylinder is like a can, like a soup can or a soda can, right? It's got a base. It's got a two-dimensional base. I'm just using page 55 or 61. I'm just using it for the diagram to write on. I'm not doing the problem on that page. So this can shape is going to be a circle on the bottom and a circle on the top. That's the base, is a circle. And let's say the radius of that circle is 4. So I just added that to the cylinder. That wasn't on the problem. If we wanted to know how much space was inside that can, how much did it hold, we would calculate the area of the base, the area of the circle. And you may remember the area of a circle is pi r squared, pi times the radius squared. So it's the area of the base times the height, just like it was with prisms. Okay, so let's say that the height is 8. Okay, let's say we're talking inches. Okay, so the unit is inches. Then the volume of that cylinder would be pi times radius squared, pi times 4 squared, which is 16 pi, times the height, which is 8. Okay. And if you multiply that out, it's 128 pi. We can leave it at pi. We don't have to convert that. So 16 times 8 is 128 pi. And the units, you guys, the units are in inches. But we have inches for the area, which would be square inches, times inches vertically with the height. So it's inches cubed or cubic inches, right? Why? Because this is a 3D object. It's got inches going in 3 different dimensions, right? Okay, so I want to show you something about something called Cavalier's principle. I'm going to show you with a little deck of cards, and then we can talk about cylinders. So I have here a little deck of these little cards, okay? And we can pretend that this is like a rectangular cylinder. The base is a rectangle. The sides go straight up, right? And so the volume, you can think of a whole bunch of these little flat rectangles stacked together, fills in the whole shape of the prism, right? It's a rectangular prism. Well, what if I did this? What if I slanted the whole thing over, right? So the whole thing was like tipped. It's called oblique. It's like tipped over, okay? The volume, you guys, is exactly the same. I have every single little layer still. I just slid them over. That's the same exact volume as if they were all standing up straight. Okay? So even if you're looking at a 3D figure that's called oblique, that's like slanted over like that, you're still just looking at the length and width of the base times the height of the stack, the height of the prism. And the same thing works for cylinders, all right? So at the top of page 64 or 58, probably 58 for most of you, we have an oblique cylinder that's kind of tipped over. Well, what if we started with a cylinder? This is the one from the other page, okay? So I'm not doing that. So what if we had our cylinder with the radius of 4 and the height of 8, right? And so if you remember, we already calculated that one. We calculated that the volume was pi r squared times 8, which was 128 pi inches cubed, right? The volume here is going to be exactly the same. The radius is still 4, the height is still 8. The area of that circle is the same circle, okay? And all those little slices of circles that are stacked up are still all stacked up here. They're just pushed over so that they go oblique, okay? All right. So I just want to show you this one last problem, and this is what if they give us the total volume and they want us to figure out, for example, what if we want to figure out what the radius is, okay? So we don't know what the radius is, but they told us the total volume. So remember, the volume would be pi r squared times the height. We know the height is 8. We know the volume is 72 pi. What we don't know is the radius, okay? So we can solve, this is an equation. We can solve this equation. We can divide both sides by 8. And what we get is 72 divided by 8. We get 9 pi equals pi r squared. We can divide both sides by pi. And we get that 9 equals radius squared. So what number squared is 9? 3. The radius would be 3 because 3 squared is 9. Okay, so that's it for today. That was a little bit long. We covered a lot of ground. And in the next lesson, we'll talk about things like cones and pyramids and spheres like balls. Okay, see you in the next lesson. Bye.